Welcome back, everyone. This slide will cover up to page 30 in your RK7 book. We will cover grain structure and changes in metals from welding. Starting on page 3, the four states of matter are solid, liquid, gas, and plasma. Metal accounts for about 24% of the mass of the planet. If not controlled, welding can alter the properties of metals, which can lead to problems. We'll start with changing from a liquid to a solid. As metal starts to solidify, nuclei, which can be seen as a base of a tree, start to form. Surrounding atoms attach to the nuclei to form a crystalline pattern, which looks like small trees. The crystalline pattern that looks like small trees are called dendrites. On page 4, the dendrites grow into each other and disappear to form grain boundaries. Grain boundaries are what develops strength in steel once it has solidified. So it would make sense that at lower temperatures, grain boundaries are stronger than individual grains surrounding them. From this, at lower temperatures, steel becomes stronger. At higher temperatures, steel becomes weaker. Here's an example of the formation of grain boundaries from a liquid to a solid. This shows grain size. The speed of cooling will determine grain size. If metals are cooled quickly, many small grains develop which create high hardness. If cooling is controlled, fewer larger grains develop which makes the metal easier to work with. If you are bending steel that has been cooled quickly, it will not deform easily and will most likely break. On page 4 and 5, there are some useful terms. You can pause this if you need to get this down. Lattice types are the structure or grain patterns that metal will assume as they cool. The three basic structures are bodied center cubic, face center cubic, and closed packed hexagonal. Here we'll start with body centered cubic. It's very common in iron and iron alloys at room temperature. It has lower malleability and ductility, which means it can be damaged much easier than the face center cubic. Bodied center cubic is referred to as ferrite. An example of this is iron and chromium. Assume body center cubic. When iron and iron alloys take on face center cubic structure, they are called austenite. This austenitic face center cubic structure is most ductile out of the three lattices, which means it can be worked and stretched more than the others without being damaged. Examples of face center cubic are iron and nickel, and iron and copper alloys, silver, and stainless steels for hospital and food equipment take on this structure. Here we got closed packed hexagonal. It's much harder than both face center cubic and bodied center cubic. This structure will only form a small amount before breaking. Examples are cadmium, cobalt, magnesium, and titanium. Getting back to pure iron, let's look at temperatures and how the metal changes. Just above 1500 degrees Celsius, crystals form into liquid form. At 1449 degrees, the steel is in a mussy stage of neither a liquid or a solid. At 1401 degrees, iron transforms from bodied center cubic to face center cubic. At this point, foundries add carbon for maximum absorption. And coming down to the Curie point, at 768 degrees Celsius, iron becomes magnetic. Page 9 and 10, when carbon is added to steels in the cooling stages around 1400 and 1300 degrees, it will remain in the mussy stage longer while it absorbs the carbon. If too much carbon is added, around 4.3%, the steel will cool much faster, resulting in a hardened state. The 4.3% carbon content is known as the eutectoid point, which is when the carbon freezes the steel. When the steel cools to austenitic stage, it is still white hot and it is still absorbing carbon. The change from ferrite, pearlite, or cementite are a relationship between iron and carbon. Cementite is one carbon atom combined with 3 iron atoms. Pearlite is a layered combination of ferrite and cementite as shown. An example of pearlite is cutting tools, high-strength wires, and knives. This diagram shows the changes from liquid to a solid. At 2800 degrees, liquid turns to a solid. One thing to jot down is that 721 degrees Celsius is the lower critical temperature of carbon steel. Quenching is when a steel rapidly cools from a high temperature. This does not allow grains to grow and produces a fine crystalline structure known as martensite. It is good to quench working tools, but as you probably know, when you quench a weld, it becomes brittle and crack sensitive. This is why you do not cool weldments that are being bent in the shop. Some of you may have experienced this. The next 3 pages are summaries with all the info from this last section. You can pause this as you need to. Moving on to page 19, we'll get into structure changes from welding. When you're welding, there can be a difference in temperature in the surrounding area of up to 1000 degrees. The 4 basic zones around a weld are the weld zone, the fusion zone, the adjacent zone, and the heat affected zone. On this diagram, the weld boundary is the adjacent zone. Page 20, root passes are prone to cracking because they absorb carbon from the base metal. This is why I tell everyone when you're working outside of the college to never leave a weld until you have the hot pass done on it. The heat affected zone can be smaller or larger depending on base metal thickness. Larger plates absorb more heat than thinner plates do, so it results in a narrower heat affected zone. The grains in welds are affected by cooling the same as steels. Single pass and tack welds have finer grains in the center from faster cooling times, and multi-pass welds recrystallize grains and relieve stresses. Figure 7, page 23 in your book shows grain structure in multi-pass welds. Moving on to page 24, when weld metal cracks, it can be from mechanical or metallurgical factors. To reduce these problems, pre- and post-heat treatments are done. Hot cracking occurs at high temperatures. It's usually from restraining the joint, welding too fast, not maintaining correct interpass temperatures, or selecting the wrong filler metal. Aluminum is pretty prone to hot shortness, which is hot cracking, and that's from using the wrong filler metal. Page 26, figure 10. High carbon steels are prone to cracking in the parent metal and usually happen around the heat affected zone. The main cause of this is introducing hydrogen into the weld. Controlling the cooling rate and pre- and post-heat treatments helps to reduce cracking. And one of the main things is to use low hydrogen electrodes. A temp stick or pyrometer can be used to measure preheat temperatures. General preheat for mild steel is between 93 and 371 degrees Celsius. Post-heating reduces the risk of cracking and is used for stress relieving finished weldments. This picture here shows ceramics for post-heating. Most places will get an external company, a stress relieving company, to come and post-weld heat or stress relieve vessels and stuff like that. Here, the next 3 slides are a summary. You can pause it as you need to, and it has all the need to know information.